Stars are certainly some of the most diverse space objects. There are hundreds of billions of stars in our galaxy, from unprepossessing red dwarves, barely visible against the dark abyss of space, to incredibly dazzling blue giants. Let's set out on a journey to some of the most outstanding ones. We will start out near our Sun, in the depth of its extremely hot corona. After that, covering hundreds of light years, we will reach the capricious and unstable Betelgeuse. After admiring its vigorous pulsations, we will move on to the dying giant CW Leonis, which is concealed from curious eyes by a thick haze of cosmic dust. And after that, we will cover another 9,000 light-years or so to get to the hottest star in our galaxy, WR102. Having passed it dangerously close, we will be on our way to the remote and weird binary star known as MY Camelopardalis. And finally, our journey will take us almost to the very center of the galaxy, to the giant star cluster Stephenson 2. It is here that the largest known star today has been detected. Let's get ready, and we begin. Kosmo. The first in outer space. On the 21st of November 2021, the Parker Solar Probe was just 8.5 million kilometers away from the Sun. It was its closest approach ever to our star. This means that it was also the first probe that got to brush against the Sun's corona, the extremely hot outer layer of our parent star. But why was it necessary to go through a number of technical difficulties and approach the Sun that close? What is Parker after that it had to get that near the star, to areas where everything around turns into ash? To realize the purpose, we have to see what we already know about our system's star. To begin with, the Sun is a main sequence star whose age is approximately 4.6 billion years. It currently falls into spectral class G2V, which on balance makes it a typical yellow dwarf. The Sun's surface temperature is about 5,800 Kelvin, which is 5,530 degrees Celsius, but it should be mentioned that there are both colder and hotter areas to be found on it. Incidentally, the star's inner layers and its outer corona are as scorching hot as millions of degrees. But for all that, they barely contribute to the visible radiation. The Sun's average diameter equals around 1.4 million kilometers, which is 109 times that of our Earth. As for the star's mass, it reaches 2 times 10 to the power of 30 kilograms, or 333,000 times that of the Earth, and actually accounts for 99.9% of the mass of the entire solar system. We're used to seeing the Sun as small, but in fact it is larger and brighter than 80% of all the stars in our galaxy that we know of. Hydrogen accounts for 92% of the Sun's overall volume. In one of our previous videos on stellar evolution, we mentioned that it is mainly this gas that fuels thermonuclear reactions for the overwhelming majority of stars when its temperature reaches incredibly high values. As they merge, hydrogen nuclei release great amounts of energy and transform into helium, which gradually accumulates in the star's center. At the moment, helium accounts for 7% of the Sun's volume and 25% of its overall mass. In addition to helium, stellar matter contains other elements as well, like carbon, oxygen, nitrogen, and iron, but their percentage is quite negligible. The Sun has an elaborate structure and is made up of several layers which differ in their properties. A massive core is at the center of the star. Estimates show its diameter to measure 25% of the Sun's overall size. The core's temperature measures as much as 14 million Kelvin, while 1 cubic meter of the material weighs around 150 tons. It is here that thermonuclear reactions, the source of energy for our star's luminosity, run their course. Every second, approximately 4.26 million tons of stellar matter is transformed into luminosity as a result of these processes. The core is surrounded by the so-called radiation zone, which continues to the point of 0.7 the Sun's radius. The density of matter in this area is too great for it to get mixed up thoroughly, and thus to carry heat to the upper layers of the star. That is why the way energy is transferred here is this. Particles of stellar plasma are continuously absorbing photons and radiating them again. Mathematical modeling shows that the temperature in this part of the star dramatically changes from 7 million Kelvin in its depth to 2 million Kelvin on the outer boundary. Estimates reveal that a quantum of light produced by the core may stay in the radiation zone from 10,000 to 170,000 years, and only then to move on to the next layer of the Sun. The one lying above, known as the convection zone, forms the Sun's outermost layer and is comparatively dense. Stellar matter here is more rarefied and changeable, which gives rise to enormous vortices in the convection zone. These vortices carry hot plasma from deeper regions of the layer to the star's surface, as it were, while plasma masses from the outermost areas, slightly cooled, move down. These convection cells remain stable for 10 to 15 minutes, after which they get destroyed to give rise to new vortices again. This continuous movement of matter creates a magnetic field, which pervades the entire inner part of the solar system. The Sun is also surrounded by an atmosphere. It is made up of several layers of elaborate structure. The lowest one is called photosphere. This area emits most of the star's visible light, so when watching the Sun, it is actually this photosphere that we see. As for its thickness, it measures from 100 to 400 kilometers, with a temperature fluctuating between 6600 and 4400 Kelvin, or between 6330 and 4130 degrees Celsius. Higher up lies a more rarefied area around 2000 kilometers thick, known as the chromosphere. It can be observed from the Earth at the time of a total solar eclipse, or else by employing special equipment. This area is extremely hot, with the temperature fluctuating between 4000 Kelvin and 20,000 Kelvin. Interestingly, its outer border is covered with spicules, continuously active jets of hot gas spurting up a staggering 5,000 to 10,000 kilometers high. The uppermost area of the Sun's atmosphere is called the corona. It consists of giant prominences, flares and emissions that may reach 1 million kilometers in size. The matter making up the corona is remarkably rarefied and incredibly hot, with an average temperature of 1 to 2 million Kelvin and the peak at 20 million Kelvin. It is this area that is occasionally crossed by the Parker probe, and every time the spacecraft immerses deeper and deeper into the blazing abyss. Calculations of the energy flow released by the photosphere will show it to be insufficient to heat the chromosphere and corona to such mind-boggling temperatures. This means that there are some physical phenomena concealed in the Sun that we have not yet discovered, which additionally heat up the upper layers. There are several scientific hypotheses that attempt to account for this thermal paradox. According to one of them, the chromosphere and the corona gain additional energy by dispersing magnetic shock waves. Another assumption explains it as an effect of charged particles' acceleration in the star's exceptionally powerful magnetic field. The Parker Solar Probe was specially designed in order to get to the bottom of these phenomena and to study obscure processes in the upper layers of the Sun's atmosphere. This probe is part of NASA's project known as Parker Solar Probe, launched back in 2009. 9 years later, on the 12th of August 2018, Parker took off from the surface of our planet on its one-way journey to the Sun to fulfill its mission. However, before getting that far, it had to execute a number of maneuvers to enter the desired orbit. By using Venus's gravity, Parker slowly adjusted its trajectory, drawing ever so closer to the scorching blazing ball in the center of our system. It was ready to withstand the star's searing heat. The probe had been designed with a heat shield, and all the equipment had been made with a view to extreme conditions to be faced. Besides, Parker's calculated orbit is supposed to lie in the Sun's immediate proximity for a comparatively short time, after which it pulls back and has a chance of giving out heat to space. This alleviates effects of thermal exposure. The probe's main task is to define the structure and dynamics of the magnetic fields in the Sun's immediate proximity. Also, Parker is supposed to gauge the energy flow emitted by the star, to capture particles of stellar wind, and to register wave-like processes in the Sun's corona. As a side mission, the probe took photos of Venus and the comet Neowise as it was drifting towards our parent star. To deal with the missions successfully, the probe is equipped with a wide range of scientific instruments like photo cameras, instruments for capturing particles, magnetometers, as well as radiation and radio wave detectors. A number of factors toward this mission. In addition to critical temperatures, the measuring instruments are exposed to an extremely powerful flow of ionizing radiation. The Sun creates strong interference in the microwave range around itself, which means that transmitting the data collected by the probe to the Earth is no easy matter either. Still, the Parker probe is carrying on with its mission. With every completed spiral of its orbit, the distance to the star shortens. In late February 2022, it is to pass through the Sun's corona yet again, in order to collect a new portion of data. By 2024, the distance between the probe and the surface of our star will shrink to become an all-time short, just 6.5 million kilometers. Estimates show that when the probe is in its perihelium, its solar shield may heat up to 1,370 degrees Celsius, which is 3 times hotter than Mercury's sunny side and only slightly lower than the melting point of iron. Even now, the probe is whizzing at a speed of 163 kilometers per second in its perihelium, but it will eventually accelerate to 200 kilometers per second, which will make it the swiftest man-made space object made so far. The probe's life expectancy cannot be that long. On reaching the closest possible point to the Sun, Parker will manage to complete several orbits around it, which is supposed to take roughly a year. All this time, it will keep losing speed, and the scientific instruments on board will be exposed to extreme temperatures and powerful radiation. Eventually, they will all be out of order, and the probe itself will descend into the scorching depths of the Sun, to be totally swallowed up by a fathomless ocean of blazing plasma. But before it happens, Parker will beam great amounts of useful data back to the Earth, which will help us make yet another step in space exploration. This is a potent proof that Parker's flight will not have been wasted. The end of 2019. Astronomical observatories report a sudden decrease in the luminosity of the star known as Betelgeuse. Observations show that its luminosity dropped to 36% of the standard value within a matter of a couple of months. Some scientists are talking about an upcoming supernova, which will be the brightest object in the night sky. Disturbingly, the gamma-ray flow emitted by the explosion is thought to be potentially dangerous for life on our planet. April 2020. Astronomers assure the general public that Betelgeuse has recovered its luminosity to the standard value. It may still go supernova at any moment, but there is no way to predict this event with any degree of certainty. Assumptions about reasons for such anomalous fading are put forward. According to the most popular hypothesis, it was caused by a giant cloud of gas and dust ejected by Betelgeuse in the direction of the Sun very recently. June 2021. The assumption is confirmed by data from Earth-based telescopes. Astronomers keep observing the object, while astrophysicists model out the processes occurring in its interior. Before we attempt to get to the bottom of what was taking place, it's a good idea to be aware of what Betelgeuse is like. This object falls into the category of red supergiants and is in the final stage of its life cycle, according to today's theory of stellar evolution. With its luminosity and radius constantly changing, its outer layers are highly unstable. The star regularly emits millions of tons of scorching gas into space, and this forms gargantuan prominences. As they cool off, they contribute to the gas nebula surrounding Betelgeuse. The star's mass is around 17 times that of the Sun, and its diameter has by now been gauged only roughly at 700 to 880 times that of the Sun. Hypothetically, if Betelgeuse were to be placed in the center of our system, it would swallow up all the planets as far as Mars, as well as most of the asteroid belt. It should be mentioned that the star has no clearly defined edge because its outer layers are extremely rarefied. Besides, the object is shrouded in a gargantuan gas nebula made up of cooled-off prominences or protuberances and particles of stellar wind. At the same time, the density of stellar matter on the conventional edges of the star is only slightly higher than that of the nebula. Betelgeuse is a remarkably bright star. Its minimal luminosity is 90,000 times higher than that of the Sun, while its maximal luminosity is a staggering 150,000 times higher. Interestingly, the star's temperature is not that great considering it ranges from 3,400 to 3,800 Kelvin, which corresponds to the red spectral band. There are barely predictable processes running in the unstable outer layers of the star. They are capable of elaborately changing the object's luminosity. The main pulsation period of the star is approximately 420 days, but less distinct cycles of longer and smaller periods can be singled out too. Besides, unpredictable flares and dimming of the star can be observed from time to time. Because this star is so unstable, it is extremely difficult to calculate the distance between us. According to the estimates offered by the Coriolis satellite in 2020, the distance between the Sun and Betelgeuse is anything from 500 to 650 light-years. According to today's notions of stellar evolution, Betelgeuse would have formed around 8.5 million years ago, and its original mass wouldn't have been over 20 solar masses. Its life cycle would have started in a giant cloud of interstellar gas that would have been gradually compressed and heated up by gravity forces. That is how the protostar, the progenitor of Betelgeuse, was born. At a certain point, the temperature and pressure in its interior reached high enough values to unleash a chain reaction of hydrogen transforming into helium. Moments later, the thermonuclear interaction consumed the entire astronomical body, and a new star flared up in the night sky. This is how the longest period in the life of any star begins, the main sequence stage. Throughout this time, merging of hydrogen atoms' nuclei that produce helium is the main energy source for them. Admittedly, the heavier a star, the faster this process runs. Life expectancy of massive stars like Betelgeuse is a measly several million years, whereas red dwarfs remain active for billions of years. Either way, over 90% of a star's life passes in the main sequence stage. Gradually accumulating, helium is drawn to the object's center to form a helium core. What happens to this star next depends almost entirely on its mass. For example, stars with masses not over 20% that of the Sun do not go supernova at the end of their existence. Unlike more massive stars, having eventually run out of almost all of their hydrogen, they slowly turn into blue dwarfs, hot and comparatively small astronomical objects. However, the minimal time it takes to complete this transformation is around 1 trillion years, which is 72 times the assumed age of the universe, which is why it is doubtful that any blue dwarf will be discovered today. After hydrogen supplies are depleted, thermonuclear reactions in the star will stop and it will become a white dwarf made up of 99% of helium. Ahead are trillions of years of slow fading and cooling until a tepid black dwarf is left instead, which is barely visible through telescopes. If an object's mass lies in the range from 0.2 to 8 solar masses, its evolution goes through more elaborate processes. Helium, which is produced as a result of thermonuclear reactions, adds to the star's core while gravity forces compress it and heat it up more and more. At a certain point, there occurs a reaction of helium nuclei merging, which produces carbon. The star begins to expand, its radius grows as well, and the temperature of the outer layers drops. In this case, the object turns into a red giant or subgiant. Comparatively light stars with masses not exceeding 50% that of the Sun cannot sustain conditions necessary for the chain reaction of helium and carbon. Transformations like these are quite irregular in such objects. As for heavier objects, reactions occurring in the star's core may run longer and produce not only carbon and oxygen, but also heavier elements, like nickel and iron. Eventually, the star sheds its outer layers, and what is left is a white dwarf enveloped in a planetary nebula. If the initial mass of the original star wasn't more than half that of the Sun, it will mostly be made up of helium, with just a small ratio of heavier elements in its composition. If, on the other hand, the star was heavier than that, the white dwarf would be mostly made up of oxygen and carbon. However, with the original star having been heavy enough, it will include neon, magnesium and even iron. Evolution of massive objects has its laws. The heavier a star, the more massive its core. With the mass of a star 8 or more times that of the Sun, its core might get over the so-called Chandrasekhar limit, which is 1.4 times the mass of the Sun. In this case, forces of internal electromagnetic repulsion are not strong enough to compensate for gravitational compression. It takes a few seconds for the core to shrink, pulling the outer layers in its wake. The exceptionally powerful compression heats up the core to temperatures of hundreds of millions Kelvin and literally crams electrons into atoms' nuclei. This turns part of the electrons into neutrons and produces great amounts of neutrinos. Even a dense material like that is not able to hold back the most elusive particle in the universe. In a few seconds' time, neutrinos break away from the collapsing star and escape, taking some thermal energy with them. As a result, the star experiences extremely powerful internal pressure, as the closely packed protons repel each other with a great force. That is why the core goes on to expand as rapidly as it shrank a few seconds previously, and this produces a tremendous shockwave in the material surrounding it. As a result, a tremendously powerful explosion occurs, which is capable of hurling the star's outer layers enormous distances away. Its flames can unleash reactions that are impossible anywhere else. That is how heavy elements are produced, like gold, lead or uranium. The nebula formed as a byproduct gradually cools off and disperses to form separate clouds, which are later compressed by gravity forces and transform into new stars and planets. Where the star has been, there remains a tiny but extremely heavy object referred to as a neutron star. If the original star's mass was over 18 to 20 times that of the Sun, on explosion its core is supposed to shrink to form a black hole, a bizarre object that distorts time and space around it. Mathematical modeling shows that particularly large stars with masses over 100 times the mass of the Sun may hypothetically be destroyed by the blast completely. In this case, all the material they are made up of will be scattered by the shockwave many light years around, or else be transformed into extremely powerful electromagnetic radiation. An electromagnetic impulse from a supernova is capable of covering hundreds of light years. At first, the radiation is characterized by incredible force, annihilating all living things on its way. However, with the covered distance growing, the density of the flow decreases and the lethal rays gradually disperse in space. Estimates show that a star similar to Betelgeuse may be a threat to anything within the radius of up to 100 light-years. It is absolutely impossible to tell when this star will go supernova, but it is likely to do so in the nearest 100,000 years. According to some estimates, Betelgeuse may flare up as brightly as the full moon. The dying star will remain the dominating object in our night sky for a while, and then will gradually fade. The object will not be visible to the naked eye anymore, and only the most powerful telescopes will be able to distinguish the radiation emitted by the tiny neutron star. If the mass of Betelgeuse is actually bigger than is assumed now, it may leave a black hole after going supernova. In this scenario, the energy flare will be by far smaller and the sight much less impressive. Either way, there is no threat to the Earth. Betelgeuse lies too far away from the solar system, and a gamma-ray flare that will accompany the supernova will not cause us any harm. The material ejected by the explosion will reach the environs of our system only in 6 million years. Its speed is estimated to be around 13 kilometers per second and will be thwarted by solar wind before getting as far as the inner areas of the system. "650 light-years away from the Earth, there lies IRC plus 10-16, a majestic star also known as CW Leonis. Its radius at its pulsation peak may reach 560 times that of the Sun, which is about 2.6 times the distance from the Earth to our parent star. With CW Leonis hypothetically placed in the middle of our system, all the planets as far as Mars would find themselves under its surface, which would even brush the inner boundary of the asteroid belt. Incidentally, the star's mass is not that great, roughly 1.5 to 4 solar masses. Its surface temperature is just 2,300 Kelvin or about 2,000 degrees Celsius. But due to its impressive dimensions, the star emits on average 8,500 times more energy than our Sun. Like any other red giant, CW Leonis is in its final life stage. Its age hasn't been defined precisely, but it is estimated to be several billion years. It is assumed that in its salad days, CW Leonis was a white-blue star with a mass 3 to 5 times that of the Sun. However, by 1 billion years ago, a great part of the celestial body's hydrogen had burned out and transformed into helium. Slowly settling in the star's center, the helium ousted all the remaining hydrogen and formed a scorching hot core which did not participate in any thermonuclear reactions. This process, typical for all stars whose mass is close to that of the Sun, is the starting point for a star's transformation into a red giant. The star's inner pressure causes it to expand to great proportions, which renders the outer layers more rarefied and unstable. The space object's diameter grows to be dozens of times greater, with its color gradually assuming a blood-red hue. A thermonuclear reaction still takes place in the star's depths, which causes the pressure and temperature of the stellar plasma to increase. At a certain point, this unleashes a chain reaction of nuclear fusion, where helium nuclei are transformed into carbon. This is the so-called helium flash. It is a complex, multi-level physical process that dramatically transforms the star's inner structure. With its core incredibly heating up, its outer layers, on the contrary, cool off and darken. There are currently great amounts of carbon in CW Leonis, but its mass is insufficient to hit the next level of nucleosynthesis. As a result, the thermonuclear combustion in the object's interior becomes unstable. The stellar matter gradually cools off and shrinks under the influence of gravitation. This heats up the star's interior again, and the reaction is unleashed with a new force. After receiving a new portion of thermal energy, the stellar matter expands again, and the combustion dies down. It is assumed that this cyclic process underlies the occasional changes of the star's luminosity. CW Leonis has a 649-day pulsation cycle, and with the luminosity at its peak is 11,300 times brighter than the Sun. With the luminosity at its lowest, meanwhile, the object emits 6,250 times more energy than the Sun. At the moment of contraction, the upper layers of stellar matter partly detach themselves from the star. This forms a carbon-oxygen gas nebula that the star is enveloped in. According to some estimates, CW Leonis loses 4 times 10 to the power of 22 tons of material every year on account of this process, an amount approximately 7 times the mass of the Earth. Observations show that the circumstellar nebula is not less than 69,000 years old, and its mass is about 1.5 times that of the Sun. As for its size, it reaches 84,000 astronomical units. The nebula has an elaborate structure with bulges and pockets of gas, as well as half arcs and irregular rings. It is posited that these formations appeared due to magnetic activity and stellar wind generated by the unstable star close by. The chemical composition of the cloud CW Leonis is shrouded in is of great interest to explorers. Spectral analysis data reveals it to contain around 70 different chemical compounds, for example carbon dioxide, water and ammonia, to name but a few. There are also quite a lot of elements from the upper part of Mendeleev's periodic table, right down to iron. CW Leonis may have had planets in the past, but they appear to have been swallowed up early on at the stage of expansion. In any event, years of observations did not reveal distinct traces of their existence in the past. What was registered was subtle changes in the star's orbit back in 1994, and more recently in 2017, mysterious shifts of matter were detected in the cloud of gas and dust enveloping the star. Some small red dwarf orbiting the giant could well account for these phenomena, although attempts to detect its radiation have so far been unsuccessful. This could be due to the nebula close by, which disperses and reflects the energy flow from sources of light located nearby. This phenomenon camouflages any objects in the immediate environs and prevents them from being accurately recognized. The mass of CW Leonis's hypothetical stellar companion is assumed to be definitely smaller than that of the Sun, and it should take it approximately 100 years to complete a full orbit around the giant. Another outstanding feature is a comparatively high water content in the star's environs and envelope. At first, it was posited that the star would melt and swallow up icy comets as it expanded. However, observations carried out in 2009 showed the temperature of some spectral lines to reach 1000 Kelvin, which is possible only on condition that water vapor forms actually in the upper layers of the giant. This fact did not fit in the model of red giant's structure accepted at the time, according to which all oxygen in stellar matter necessary for water synthesis must be used up completely to produce carbon monoxide. A new hypothesis was put forward to account for the witnessed phenomena, which stated that molecules of silicon oxides and carbon are destroyed by a powerful ultraviolet radiation. After that, the released oxygen reacts with hydrogen and there forms scorching hot water vapor. The weakness of this hypothesis is in the failure to account for the source of ultraviolet radiation. Reactions like that may occur only in rather high temperatures, that is, within stellar matter. However, it is practically impervious to cosmic rays. This paradox may be explained by yet another assumption. Since the star is unstable, large ruptures and low-density areas occasionally occur on its surface, where ultraviolet radiation is not blocked out that effectively. The water vapor's overall mass in the star's atmosphere and outer layers is estimated at several quintillion tons. Enormous though this figure may seem, in fact, water accounts for just around a billionth of the star's overall mass. According to today's notions of stellar evolution, being a red giant, CW Leonis is in its autumn years now. It will deplete its stellar fuel in the next 10 to 30,000 years, after which it will discard its outer layers following a powerful explosion. It will transform into an incredibly hot and dense space object, a white dwarf. Its mass will be roughly 80% that of the Sun, and its temperature will reach several million degrees in the first seconds after the transformation. However, with no energy source, it is destined to slowly and irrevocably fade in the course of billions of years to follow. Eventually, the celestial body will be almost invisible against a background of cosmic emptiness when it becomes a mysterious black dwarf. But this will not happen anytime soon. The shockwave and the mind-boggling temperature in the epicenter will generate new elements that are not to be found in a star's interior. For example, uranium, gold and lead. They will later become part of new celestial objects. Millions of years later yet, radioactive decay will heat the planet's interiors, melt the ice, and saturate the oceans with microelements, thus creating conditions for the genesis of life. The universe is constantly evolving, and global cataclysms and destruction are an inalienable part of this process. But at the end of every storm, there are fresh rays of light. Temperatures of any star's interiors are incredibly high. It is hardly surprising, as thermonuclear synthesis, that is the main energy source of all stars, can take place only in these extreme conditions. When two atoms of hydrogen merge, they produce an atom of helium and release an electron and several neutrinos. In addition, a great amount of energy is released during the process. Still, the hydrogen-helium synthesis isn't the only process that heats up stars. At higher temperatures, other elements may take part in chemical reactions as well, for example lithium, carbon or oxygen. In this case, cores of heavier elements are produced, such as sulfur, magnesium or phosphorus. Their charge is higher and they repel each other more robustly. Much more energy is needed to overcome this resistance. When a main sequence star depletes most of its hydrogen supply, it starts to expand and cool off. With time, it ends up as a red giant. It will continue to burn due to thermonuclear reactions of helium transforming into carbon and oxygen. The lighter the star, however, the less time it will continue to burn. Eventually becoming unstable, it sheds its outer layers and goes supernova. This leaves it a white dwarf with no resources to fuel any thermonuclear reactions anymore. With all its energy sources depleted, it is forced to gradually cool off. Interestingly, when the mass of a star is higher than a certain value, heavy thermonuclear synthesis may become the star's main energy source even after all hydrogen has been used up. Such celestial objects are referred to as Wolf-Rayet stars. This class of space objects was discovered back in 1867 by the French astronomers Charles Wolf and Georges Rayet. The scientists' attention was caught by anomalously bright emission lines of heavy elements in these stars' spectra. As for the inner makeup of these unusual celestial objects, it was accounted for much later. Stars of this class are generally heavy. They have quite a meager supply of hydrogen and are in the final stages of their evolution. Wolf-Rayet stars are extremely rare. To date, just a few hundred of them have been discovered in our galaxy. As for their overall count in the Milky Way, it is estimated that there can't be over 2,000 celestial objects of this class. Wolf-Rayet stars are subdivided into three main sequences depending on the prevalent element in the spectrum: nitrogen, carbon and oxygen sequences. Each of them, in its turn, is subdivided into several types. As for the hottest star in the studied universe, it falls into the category of the oxygen spectral sequence ones. The celestial body, which is now known as WR102, was discovered back in 1971. At first, it was mistaken for the optical counterpart of the X-ray source GX3+1. However, further observations revealed that there were two completely different objects. According to data acquired thanks to spectral analysis, the discovered star had unusually bright oxygen lines in its radiation spectrum. Thus, in 1982, WR102 and four more bright stars became the first to form a new class. Spectral analysis showed that the star's surface temperature reaches over 210,000 Kelvin. This makes WR102 approximately 36 times as hot as our Sun. The luminosity of this scorching hot object is unbelievable. It is estimated at over 380,000 times that of the Sun. WR102 lies about 10,000 light-years away. The star is located in the part of the sky with the constellation Sagittarius. Incidentally, in spite of its exceptionally high luminosity, it can't be seen with the naked eye, as it is too far away from us. WR102 currently belongs to the extremely rare star class WO2. Containing great amounts of oxygen and almost no hydrogen, it mainly relies on the merging of heavy cores of such elements as neon, carbon and oxygen as its sources of energy. To date, only 9 objects of this class have been discovered, with 4 of them located in the Milky Way and the other 5 in other galaxies. There are 2 factors that make oxygen spectral sequence stars rare. Firstly, there are very few of Wolf-Rayet stars around because only stars with a mass not less than 40 solar masses are potential candidates to become ones. Secondly, this class represents the final stage of evolution of stars of this type. The stage may last anything from 1,000 to 10,000 years, which is mere seconds in astronomical terms. Being of comparatively modest dimensions, WR102 is notably quite a dense star. With its radius measuring just 58% that of the Sun, its mass, on the other hand, is estimated at 15 to 18 solar masses. On its birth, it is thought to have been as heavy as 40 to 60 solar masses. Still, the high temperature and robust chemical reactions in the star's interior cause an exceptionally powerful stellar wind, whose particles' velocity is over 5,000 kilometers per second. It takes WR102 just a few months to lose 1 Earth mass worth of material on account of its stellar wind. At this rate of particle emission, the star is going to lose 1 Sun mass worth of material in the course of 10,000 years. There are no planets orbiting WR102, but it is shrouded in a gas envelope. Not dense and exposed to powerful ultraviolet radiation and strong stellar wind, the envelope gets contracted and ionized, which sustains its elaborate structure of protuberances and arches all around the star. According to a proposed theory, the gas cloud around WR102 may probably be remnants of the former hydrogen outer layer of the star. Another theory maintains that the cloud came to be as a result of the particle flow emitted by the star. WR102 is not the only outstandingly blistering place in the universe. For example, WR142, WR30A and WR93b, as well as the central star in the Bug Nebula NGC 6302, are as hot as around 200,000 Kelvin. Some white dwarfs may have almost the same surface temperature. However, all these are no match to neutron stars. When neutron stars are born, their temperatures may reach a staggering 100 billion Kelvin. Active neutrino emissions cool them off comparatively rapidly. But either way, the surface temperature of any neutron star is never less than a few 100,000 Kelvin. As for their cores, they must, admittedly, be hotter still. Having said that, it is highly improbable that the ultimate temperature record is ever going to be beaten. According to today's cosmological concepts, the temperature of the universe at the moment of the hypothetical Big Bang was approximately 1.4 times 10 to the power of 32 Kelvin. A fundamental physical constant, this value is referred to as the Planck temperature. Contemporary physics is not capable of defining a substance of a higher temperature, as physical laws are distorted beyond any recognition in such incredibly harsh conditions, quite beyond our imagination. Getting back to WR102, judging by the data we have on stellar evolution today, this star is in its autumn years now. As opposed to main sequence stars, Wolf-Rayet stars do not expand in their final stages of life. Their substantial mass holds all the star's material together in a dense and hot ball. However, after losing a lot of its mass through stellar wind, the object will eventually get destabilized. If current estimates are accurate, WR102 appears to be ready to go supernova at any point in the next 1,500 years. Bearing in mind that the distance between the star and the Earth is 10,000 light-years, it is highly likely that the event has already taken place. A supernova would have been accompanied by an extra-powerful gamma-ray flare. Fortunately, our planet is too far away to suffer any pernicious effects of this dangerous emission. WR102 is comprised of rather heavy chemical elements and even iron. Its later evolution will force it to contract to a critical point. The great explosion bringing the star's life cycle to a close will unleash processes of robust proton and neutron capture. This way, still heavier elements form, including transuranium ones. Eventually, WR102 will be replaced by a neutron star, a celestial body unbelievably hot and dense. The former star's outer layers, disrupted by the explosion, will form a nebula. Slowly cooling off, it will give off heat to the space around it. Many billions of years later, this material will be able to form a new planetary system. This binary system has been on the astronomical map for several decades, and all the while has been thought of as just one super bright star. MY Camelopardalis, or MY Cam for short, is 13,000 light-years away from the Earth. It used to be classified as a variable star. The object aroused interest only as late as in 2014, when a group of Spanish scientists was able to define MY Cam as a binary star system. The discovery was made thanks to a 2.2-meter telescope in the Calar Alto Observatory. Both stars boast a comparatively big mass and are drawn quite close together, with their outer atmospheres almost touching. One of them is 38 masses of our Sun, and the mass of its companion is 32 masses of our Sun. The radius of each measures 700 those of our planet. Just to compare, it's 6 times the radius of our Sun. As for the age of these objects, they're comparatively young and cannot be over 2 million years old. MY Cam may well be called one of the most massive binary star systems known to science. Both objects of the system are hot blue O-type stars. Their rotation speed may reach up to 1 million kilometers per hour, with the surface temperature of each of them as high as 40,000 kelvins. The orbital period around their common center is about 28 hours, which means that both giants complete a full orbit around each other in a bit over a day. Just to compare, our Sun completes one full rotation in 26 days. MY Cam is also quite bright, which makes it visible even through a common telescope. The star's orbit is a rather narrow one, which is why they're alternately eclipsed practically every day. This explains constant changes in their luminosity. Before this fact became known, scientists used to be confused about the properties of this stellar system. The existence of MY Cam doesn't seem to be that incredible, considering the fact that most celestial bodies in the Milky Way were formed in big stellar systems whose objects were also variable and eclipsing stars. This means that these objects' overall luminosity may vary from time to time. MY Cam can be called one of the best-known stellar systems of the kind. In fact, it seems to have been originally formed like this, and has always looked the way we can observe it today. Since the components are in such close proximity, sooner or later they are bound to collide and then merge into one enormous star whose mass may well reach as much as 60 sun masses. Thanks to theoretical modeling, it is assumed that when stars merge, it is a quick procedure accompanied by a big bang, with incredible amounts of energy released as a result. If this happens with MY Cam, astronomers will be able to observe this demonstration, confirming the theory that supermassive stars are formed when two less massive objects merge. To date, science has not yet witnessed a merging process of this kind. The possibility of our suns taking part in a similar process is quite negligible. According to today's estimates, a collision of the main star of our system with another star may take place once every 10 to the power of 28 years. But even with such a minuscule chance of this collision, our Earth would be seriously affected were it to take place somewhere close by space standards. If it were to happen within 100 light years from us, our blue planet would be completely devastated. However, at this point there isn't a single star cluster within that range. So far, we have only been able to record the result of two neutron stars' collision. In theory, this process should result in the formation of a neutron star with an even bigger mass, or else it should cause the formation of a black hole. When merging, neutron stars are capable of generating a magnetic field billions of times more powerful than that of the Earth. This process may be accompanied by a gamma-ray flare. That is the most powerful energy emission in the universe known to us. I mentioned it at some point in other videos. However, in spite of the tremendous scale of this phenomenon, astronomers have never been able to directly observe the process of merging stars. One of these events, the GRB 150101 gamma-ray flare, was detected only in 2018. The event made it possible to draw a connection with gravity waves detected back in 2015. Gravity waves are also a result of two neutron stars merging. It looks like something similar awaits MY-CAM as well, and if a planetary system were in its vicinity, it would be a far less serene place to be around in comparison with our planet. The enormous mass of MY-CAM is indicative of its short life, which leads us to assume that intelligent organisms would simply not have had enough time to develop on its hypothetical planets. Besides, as the stellar system grows older, both its components increase in their dimensions. This process brings MY-CAM ever closer to its inevitable destiny of becoming a supermassive stellar giant and then an even heavier neutron star or else a black hole. The MY-CAM system is also peculiar for the fact that it is located in a region of the universe rather densely filled with stars. Regions like that are sometimes referred to as globular star clusters. Star mergers are rather common in areas of this kind, since the number of stars there is by far greater than in our system's proximity. According to the latest estimates, star collisions in globular star clusters occur approximately once every 10,000 years. Unlike MY-CAM, objects like our Sun are sole drifters in a galaxy with only a planetary system for company. However, such celestial objects are not that common in the universe. Sun-like single stars in the Milky Way account only for a measly 2%. Most stars are part of multiple systems. For example, triple star systems are the most common, accounting for about 75% of all observable stars. Most of them have to struggle with the gravity force of their companions throughout their lifetime. This interaction, in its turn, leads to the formation of even larger stellar systems. Most of the supermassive stars known today may at one point have been part of systems with at least one companion of an identical mass. Thanks to frequent eclipses occurring in multiple star systems, scientists are able to investigate the celestial objects in more detail. In the case of MY-CAM, for instance, astrophysicists detected a wide range of spectres of light emanating from it. They went on to use the Doppler effect, thus measuring the star's orbital speeds. With this knowledge, it was safe to maintain that MY-CAM is an exceptional object in space. In the future, this stellar system will enable us to confirm some hypotheses as to the formation of massive stars in our galaxy. Until a short time ago, it was UY Scuti that used to be considered the largest star known to mankind for a long while. Located 9,500 light-years away from the Sun, The star is so staggeringly enormous that it would cover areas beyond Jupiter's orbit were it placed in the center of the solar system. Its radius may reach 1,900 those of the Sun, and its volume may be over 5 billion times that of the Sun. However, recently a new giant has claimed the title of the largest star in the known universe. It is known as Stephenson 2-18, or RSGC 2-18. The star lies approximately 20,000 light-years away from the Sun and is part of the open cluster Stephenson 2, although according to some scientists, this space object should not be associated with the Stephenson cluster, as it wouldn't be accurate. Either way, Stephenson 2-18 is located in the Scutum constellation and continues to bear its original name. The star itself was catalogued in the All-Sky database back in the 1990s, but giant clouds of cosmic dust largely interfered with observation of the star clusters in the Scutum constellation, obscuring them from any observer anxious to find out more. Only in 2020 were scientists able to acquire data about its size, and the information proved to be astonishing. According to some estimates, the radius of Stephenson 2-18 may reach up to 1.5 billion kilometers, which is 10 times the distance from our Earth to the Sun, or 2,150 times the radius of the Sun. This means that the supergiant's volume should be about 10 billion times that of the Sun. Placed in the center of the solar system, Stephenson 2-18 would easily swallow up Saturn, along with all of its rings and moons, to say nothing of the terrestrial planets. Interestingly, it would take light almost 8.5 hours to travel the length of this gigantic star's equator. This is the same time it takes sunlight to reach Pluto at the remotest point of its orbit. The supergiant's luminosity is estimated to reach 440,000 times that of the Sun, although its surface temperature is comparatively low at about 3,200 Kelvin. This is about 2 times as little as that of the Sun, and corresponds to the red band of the light spectrum. This is the reason why Stephenson 2-18 falls into the category of red supergiants. Also, this relatively low temperature implies that most of the star's radiation is in the visible and thermal spectra, with amounts of deathly ultraviolet and X-ray types of radiation rather negligible in comparison. It may seem strange that in spite of its impressive dimensions and sufficient luminosity, Stephenson 2-18 cannot be seen from the Earth with the naked eye. But this has to do with its low surface temperature as well as clouds of stardust and gas shrouding the giant star, thus concealing it from observers on our Earth. They absorb and disperse the star's light, and this poses difficulties for studying the object. The mass of Stephenson 2-18 still remains to be gauged. However, supposing its inner makeup is similar to that of UY Scuti and other supergiants, it should be anything within 20 solar masses. If it is the case, the average density of supergiants like that must be extremely low and almost equal to the density of the Earth's atmosphere at a height of about 90 kilometers above the sea level. That is practically on the border with space. It is really amazing that thermonuclear energy, that is the kind of energy that gives a glow to a star, is still sustained in such conditions. Supergiant sizes are so mind-boggling that these objects are hardly steady. Most of them are variable in terms of their luminosity, and as a rule this variability is unpredictable. No wonder, as the overwhelming majority of supergiants are in the final stages of their life cycles, which means that they may go supernova literally at any moment. According to the contemporary scientific concepts of stellar evolution, it is stars with original masses from 10 to 40 that of the Sun that qualify to become red supergiants at a later stage of their existence. Thermonuclear reactions in their interior rapidly burn out all hydrogen, thus turning it into helium. After that, fusion reactions of helium, carbon, oxygen and lithium become the chief energy source of the star. Life expectancy of stars of this kind is comparatively short, just a few million years. As it evolves, the prospective supergiant rapidly expands in size and loses its mass on account of strong solar wind. Clouds of stardust and gas surrounding the original star are quickly absorbed by the new star, which keeps swelling way beyond its original size at an astonishing rate. However, its own solar wind creates a new nebula around the star. On account of the short lifespan of this kind of star, no planets can realistically originate in this nebula. Eventually, the supergiant explodes. Following the supernova or even hypernova event, the outer layers of the star are hurled away and then gradually cool off, forming a nebula. As for the former core, it becomes either a neutron star or a black hole depending on its mass. By the way, feel free to see our previous videos about dwarf stars and supernovae. A hypernova event is accompanied by a high-energy X-ray burst, powerful enough to eliminate any life within the radius of several light-years. Luckily for us and the Earth, all supergiants identified by scientists so far lie considerably further than that, so we seem to be safe from those. Due to active radiation of charged particles, the rotation of stars of this type gradually slows down, and eventually their outer layers practically grind to a halt. The core of the star, meanwhile, continues to rotate quite unabated, and there may be a substantial difference between the speed of the core and that of the outer layer. Taking into consideration the high luminosity, low temperature and impressive dimensions, on balance, it is safe to assume that the habitable zone of Stephenson 2-18 should be really huge. Its middle should lie approximately 663 astronomical units away from the star's center. In other words, 20 times the distance from the center of the Sun to Pluto's orbit. And as for the area of the habitable zone, it is expected to be 1 billion times that of the Sun. Scientists do admit of the possibility of the existence of planetary systems around supergiants. But what with these stars' short lifespan and unstable conditions, the chances are almost negligible. At any rate, no confirmed exoplanets have so far been discovered in the environs of one. Stephenson 2-18 lies so far away that its light travels to our Earth for 20,000 years. For all we know, at this very moment its core might be shrinking to form an extremely dense neutron star, with red-hot shards of outer layers flying away in all directions to become part of ice-cold space. But mankind will be able to find this out only in a very distant future. There is no doubt that this is just a minuscule portion of the infinite diversity of the amazing stars making up our galaxy. It would take us millions of years to cover all of them. Meanwhile, there are countless other galaxies across the expanses of the cosmos, each containing great numbers of objects just as worthy. And this may only mean that our journey is not over yet. Let's keep in touch.